Quantum leap. Physicists successfully simulate super diffusion. Quantum physicists at Trinity, working alongside IBM Dublin, have successfully simulated super diffusion in a system of interacting quantum particles on a quantum computer. This is the first step in doing highly challenging quantum transport calculations on quantum hardware, and, as the hardware improves over time, such work promises to shed new light in condensed matter physics and materials science. The work is one of the first outputs of the TCD IBM Predoctoral Scholarship Program, which was recently established, where IBM hires PhD students as employees while being co-supervised at Trinity. The paper was published recently in the leading Nature journal, NPJ Quantum Information. IBM is a global leader in the exciting field of quantum computation. The early-stage quantum computer used in this study consists of 27 superconducting qubits. Qubits are the building blocks of quantum logic, and is physically located in IBM's lab in Yorktown Heights in New York and programmed remotely from Dublin. Quantum computing is currently one of the most exciting technologies and is expected to be edging closer toward commercial applications in the next decade. Commercial applications aside, there are fascinating fundamental questions that quantum computers can help with. The team at Trinity and IBM Dublin tackled one such question concerning quantum simulation. Explaining the significance of the work and the idea of quantum simulation in general, Trinity's Professor John Gould, director of the newly established Trinity Quantum Alliance, who led the research, explains, generally speaking, the problem of simulating the dynamics of a complex quantum system with many interacting constituents is a formidable challenge for conventional computers. Consider the 27 qubits on this particular device. In quantum mechanics, the state of such a system is described mathematically by an object called a wave function. In order to use a standard computer to describe this object, you require a huge number of coefficients to be stored in memory, and the demands scale exponentially with the number of qubits, roughly 134 million coefficients, in the case of this simulation. As you grow the system to, say, 300 qubits, you would need more coefficients than there are atoms in the observable universe to describe such a system, and no classical computer will be able to exactly capture the system state. In other words, we hit a wall when simulating quantum systems. The idea of using quantum systems to simulate quantum dynamics goes back to the American Nobel Prize-winning physicist Richard Feynman, who proposed that quantum systems are best simulated using quantum systems. The reason is simple: you naturally exploit the fact that the quantum computer is described by a wave function, thus circumventing the need for exponential classical resources for storage of the state.